In this video, we're going to be programmatically detecting candlestick patterns using TA-lib and then passing that through to VectorBT to backtest our strategies and establish once and for all whether candlestick patterns actually work as a trading method. We're going to be using a really simple strategy in this video just to show you the idea, and then you can expand on that yourself. We're just going to be using a hammer candlestick pattern, which signals a reversal. And then there's the opposite of this called the hanging man, which is the same thing just in an uptrend, which signals a bearish reversal. To implement all this, we're going to be using TA-lib, as I mentioned earlier, which is a blazingly fast technical analysis library that's super simple and easy to use, a real must-have in your algo trading toolkit. And we'll also be using VectorBT to actually process the backtest itself after we've calculated our entry and exit points. So it's going to take about 20 minutes here to get us up and started backtesting candlestick strategies. So strap yourselves in and let's dive into Python. So let's boot up a terminal here. I'm in a virtual environment here that's got VectorBT installed, as well as requests and a few other libraries. You can easily install all of them with just pip install VectorBT, or however you install packages in your IDE, whether that's Jupyter Notebooks or Visual Studio Code or something similar. Once we've done that, we can go ahead and actually get started here. So I'll just call a file tutorial.py. And we want to do some importing here. So you'll need VectorBT to actually do the backtest as VBT. We'll import yfinance just to get some data here. Feel free to use your own data source, obviously, if you have a nice SQL or timescale database on hand. We'll also be using TA-lib. Now, TA-lib can be a pain to get installed, so if you're having any real difficulties with it, I will provide some links in the description that you can check out to install TA-lib on your respective operating system. So that should be enough just to get us started here, and let's go ahead and just grab some data quickly from Yahoo Finance here. So data equals yf.download. And then you want the symbol, so I'm going to use BTC USD. I like to use crypto data because it trades 24/7 and there's just fewer problems with it, especially for candlestick detection. You're going to get nice, clean candlestick charts because there are no gaps in the data. We'll then want a start and end date. By default, it's going to grab daily data. So if I say 2020-01-01, and we'll say the end date is going to be 2022-01-01. So I'll grab daily data for Bitcoin USD for those dates. That's great. Let's print that out to make sure it's actually arriving here. Okay, so we've got our open, high, low, close, which of course we can use to reconstruct a candlestick chart, and that's what TA-lib's going to read to find our hammer pattern here. So we'll go ahead and just run that here. So we can say hammer is equal to TA-lib.cdl hammer. So you may wonder where I've just pulled this function from here. If you go back to the TA-lib documentation here, there's a big long list somewhere near the bottom here. So you can see down here, pattern recognition. There's all these different common candlestick patterns. Unfortunately, if the candlestick pattern you're after isn't listed in this particular file, then you're going to have to implement it yourself. But to me, this seems rather complete, at least in terms of the varying candlestick patterns that you can get. So as I mentioned, we're going to be looking at the hammer pattern here. So the main body of the candle is on top, and then there's a big wick below it, basically. We'll need to keep this in mind because obviously we want to check that the pattern recognition's actually working. Moving back to our file here, so we have TA-lib.cdl hammer, as I mentioned before. You'll find it in that big list of functions. You'll then want to pass in the parameters. So in our case, it just requires the open, high, low, close. So you can do data.open, data.high, data.low, and data.close. And then if we print out hammer here, and we'll comment out this printing of data here. So what this is going to do is it's going to print either 0, 100, or minus 100. So if I go hammer, but I only want it where hammer is equal to 100. So this will only give me the dates where the value of hammer is 100, meaning it's a bullish signal. So you can see we've got maybe 20 data points here. Let's just pick one of these at random and see what happens. So 2021, 11/06. Let's go have a look at that date on TradingView here. Now, depending on what time frame you're using, the data might slightly differ with something like TradingView. So you want to keep that in mind. I've already forgot the date here. 11th of the 6th, 2021. So let's go have a look at that down here. This one. Yep, so we can see this looks like a hammer here. So it's on a downtrend, high body, long tail, and then an uptrend. So that seems to be working rather well. Let's just check another one here. Probably slightly redundant, as I'm sure the TA-lib guys have done their job, but just to make sure our data sources are working. So August the 22nd, 2020. So yeah, this is a similar sort of pattern. This is arguably less like a hammer, but I think it probably fits within the textbook definition, whatever these guys have used in their implementation of these different patterns. Regardless, it's good enough for a demonstration. If you're wondering how I knew that it would output 100 there, or how I knew to input open, high, low, close, the documentation for TA-lib is actually contained within this help function here. So if you open up a regular Python terminal, you import TA-lib, you can type help and then the function, so TA-lib.cdl hammer. And it'll pull up a little help page here with the different inputs and outputs at least. So we know it takes in open, high, low, close, and the values it can output are -100, 0, or 100. Now, it's not listed anywhere, but from experimentation, I found that indicators give 100 for a bullish signal, 0 for nothing, and then -100 for a bearish signal. So for example, if I look at values where the hammer is -100, you won't find any, no matter how much you search, because ultimately the hammer is always signaling a bullish reversal. So it's always going to be a positive number. So this is going to give us our buy, which means we need something to tell us when to sell. And for that, we're going to look for the hanging man candlestick pattern. So this is going to be much the same as the hammer here. So it's just hanging man is equal to TA-lib.cdl hanging man. And then we just pass in data.open, data.high, data.low, and data.close. So once again, very simple. TA-lib makes our life very easy as long as the pattern that you're looking for is actually in their database. So let's do the same thing here, except instead of hammer, I'm going to use the hanging man. Now, of course, this is a bearish reversal sign, so it's going to signal -100, telling us that we should turn bearish at this point, if we believe this signal, of course. The hanging man looks exactly the same as a hammer, it just comes at the top of an uptrend rather than the bottom of a downtrend. So let's go have a look. So this is 12/06, okay, 2021. I'll actually look for one in 2020 here. So August 23rd. Let's go have a look at that one. Yeah, so this is sort of what we're looking for. Although, again, it's got a little bit of a top there, but roughly this is what you're looking for. Obviously, in this case, the trend continued a little bit further and did eventually reverse, but I'm not entirely sure that this candle was the reason for it. So let's go back here. Now that we've got our entries and exit points, we can set about backtesting this. Easiest way to do that is just to create a buys and a sells series here. So the buys is just going to be equal to, we just want where hammer is equal to 100. We just want all those values. And we want to do the same thing on sells here. Very, very simple. So hanging man is equal to -100. You can, of course, chain this logic and do all kinds of crazy stuff. You know, you can say where the hanging man is equal to -100 and the RSI is greater than 50 and various other things. In this video, I want to just focus on candlestick patterns so that we can add that tool to our toolkit. To make sure this is working, I'll just print out the buys here. And so you can see what the format looks like. So basically, it's just a Boolean series of true or false values for every day. Obviously, if it's true, that means we buy. Equally, a true value in sell here would mean that we sell at that time. Now, the backtest itself in VectorBT, well, it's just one line, really. So we say PF for portfolio. That's equal to vbt.portfolio.from_signals. And then we just pass in our closing data, our buys, and our sells. You are going to want to be a little bit careful with which data you pass in. So whether you pass in the open or the close. The reason being that VectorBT is going to execute the order directly on the bar that it says true. So for example here, if this were true, it would buy it at the closing price on this date. One of the problems with that, however, is that you don't actually know that the candlestick pattern has formed until this candle has completely finished. And if we were trading stocks, well, at the end of that candle, it might be the end of the day, so we can't actually put an order through, and so you'd actually want to provide the next day's open price. For Bitcoin here, it doesn't matter so much because we're trading 24 hours a day, and we can check in a little bit for look-ahead bias, but that's just something I wanted to make you aware of, just to make your backtests a little bit more realistic. So we'll go back here to tutorial, and let's go ahead and just print out pf.stats. That'll tell us how our backtest does here. So we're buying on the hammer, and we're selling on the hanging man. Let's have a go. So let's have a look at our strategies here. So we can see that our end value here was 188, starting with the initial capital of $100. That means we made 88%. However, unfortunately, the benchmark return was 562. So we massively underperformed the benchmark here. Although maybe if we have a look at the chart, perhaps we had less time in the market, which might make it a more interesting strategy. So let's have a look at that. And we can see that by doing pf.plot.show. And I'll cover this up here. So if we look at this strategy here, we can see that it's not exactly keeping us out of the market very long. It enters very quickly after it exits, meaning that it's not even really protecting us from volatility to make up for the lower returns that it's making. So that's not going too great. And we haven't even added fees into the mix yet. Let's change up the data source a little bit to try hourly candles and see if that performs a little bit better. So in order to do that, I'm going to import date time here. So from date time, import date time and time delta. This is just so that we can tell Y Finance what range of data we want to download. The last bar here is just going to be the end time, which is going to be date time dot now. And then the start time is going to be the end time minus the amount of days that we want. So time delta, let's just say days is equal to 5 or 3, 4. We'll sell for 4 days of data here. So the start is going to be the start time and the end is going to be the end time here. So we're just taking the hourly bars from 4 days ago to right this second. And obviously we have to tell it that we want hourly data. So you do that with interval is equal to 1h. Now, Yahoo Finance will only give you hourly data for, I think, about a month. So obviously that can be a little bit restrictive. And I'll print out the stats here so that we can see what it looks like. So if we check out the stats here, we can see it's performing a lot better, at least on this initial backtest. It seems to be doing slightly better than the benchmark, although that is, of course, before fees. We can see what the impact of that would be by just going in here and saying fees is equal to, let's say, 0.5% as a decent rate for crypto fees. And we'll see what that does to the profitability of the strategy. It's still beating the benchmark though, which is nice, although can very much be a statistical oddity. So let's crank this up again and maybe we'll test the past 20 days of data, see how that works. At least we drew down less than the benchmark here. And so I'm hoping you can see how you can test out different variations of this strategy. You know, maybe you want to switch this for a different one. You want to change the time frame that we test it over, the interval. Many different parameters are going to go into creating a potentially winning strategy here. So what I'm going to do here in the next 10 minutes or so is take this a step further. Now that I think I'm potentially on to a winning strategy, I'm going to test it over lots and lots of different 1 hour windows to make sure it's not just luck that the time frame I'm testing it on, that being the last month, the last few days, just to test that that isn't pure luck. As always, if you need any help backtesting your strategies in Python, links are down in the description for my coaching and consulting services. So let's get going here and test this strategy a little bit more to make sure that what we've actually found is statistically significant and not just some random fluke. In order to do that, we're going to need a lot more data than Yahoo Finance can provide us here. And so I'd recommend going to cryptodatadownload.com. Of course, you can use your own data if you have a database handy, or if you followed any of my other tutorials on how to scrape data. But if you just want a super simple historical data download, you can go over here to cryptodatadownload.com, and they have a few exchanges here. I think Bitstamp works quite well. So if you go Bitstamp and then you go US BTC USD, download the hourly here. That's the file that I'll be using in this video. So I'll download the CSV. I'll overwrite the one I've got already just so I can show you. Replace. So if we open up that file, what we have is, well, firstly this header, we need to get rid of that so that Python can read it properly. We've got the Unix time here, which is the number of seconds since the 1st of January at midnight, 1970. We've got the date here in a more human readable format, and then open, high, low, close volume. So that's all the data we really need here. Let's go ahead and just pull this into Python. I'll go through this a little bit quickly because I assume that you're quite familiar with grabbing data and that you've done this thing 100 times before, or else you might even have your own data source, in which case this isn't even relevant for you. So we get rid of this start and end time here, and I'll just go data is equal to pd.read_csv. It's going to be bitstamp underscore BTC USD 1 hour.csv. Okay, so we've got our CSV loaded. If I go ahead and print that out, so print data, just check it's loaded. PD is not defined, so I need to import pandas here. Imports pandas as PD. So great. The next thing we need to do is convert that Unix time there to an actual date time format. It's pretty easy to do. Use the date time, select the column. So Unix is equal to pd.to_date time data Unix. I'll print this out again just to show you. You can see here that this has now turned into a date. Now, it has set it to 1970 here, which is what you might not expect. That's just because Pandas assumes that the Unix timestamp is in nanoseconds and ours is in seconds. So you just need to provide an S there to tell Pandas that we're counting in seconds here. Once that's done, we need to set this column as the index. So it's going to be in a very similar format to the Y-finance data that we initially used. And to do that, you can just do data.set_index, the column that you want to set as the index, and then in place is equal to true. And that'll just change the actual data frame. So if I print it out, we've now got our dates here as the column on this side, which is great. You'll also notice our data is the wrong way around, just happens to be the way that Crypto Data Download does things. So you'll want to reverse this data before you do any backtesting, otherwise you will end up with some rather strange results. So in order to just reverse the direction of things, you can just do data is equal to data.eloc and then provide a slice here that'll just reverse everything. While I'm here, I'm just going to get rid of the other columns as well. So I'll do data and I'll just grab open, high, low, and close. We don't really need those other columns. So everything's in the right order now. We're in ascending date order and we have open, high, low, close. Now, the rest of this script is going to complain here because these are not capitalized. To fix that real quick, you can just edit the actual column values. So you can say columns is equal to, give it a list, open, high, low, and close. So we're basically just changing the names of these four to these four just to make the rest of my script happy here. Now, if I just leave things as they are, if I run things, it should just do one massive backtest here with about 4 years worth of data. So we'll see how that goes. Not great judging by these statistics. The total return is minus 74%, whereas the benchmark is up 134%. So using this strategy over a long period of time, it doesn't seem to be working out so well, at least not in Bitcoin, although maybe it does work for other assets, and maybe that's something you'd like to look at. So as you can see, our profit and loss distribution's all over the place, and we're massively underperforming the benchmark here. Still, this is just an example, so it's not too much of a worry. Just to confirm things here and to make sure that this strategy is actually as useless as we think it is, let's use the method I alluded to earlier, where we're going to run this backtest on 10-day windows throughout this whole period. So I have about 4 years worth of data. We're going to test the strategy on every 10-day window from that period. So for example, we'll test it from the 1st of January 2021 to the 10th, and then from the 2nd to the 11th, then from the 3rd to the 12th, so on and so forth. We'll keep testing it and we'll record exactly how much money we made. And that way we'd have a much more realistic idea of how this strategy performs in different environments, as we've basically gone through one full crypto cycle during that period. So let's get to work here. I'm going to do things with a really basic for loop here in Python. If you want to get fancy and crank out the maximum speed from VectorBT, it is possible to do this in a vectorized format, but we'll be here an awful long time trying to get the logic sorted out. So let's just use a basic for loop here, keep things nice and simple. The speed's good enough anyway, given that VectorBT is compiled for us with a number. So a simple for loop for x in range, and then we're going to want the maximum here to be the length of our data minus the window length, and we'll go in 24 steps. So we'll check every single day. We need to define a window length, and that's going to be 240 hours is just 10 days. So what this is saying is run this simulation lots of different times. What we need to do here is we need to trim down this data. So I can come in here, I can just make a new variable here. I'll call it window data. And that's going to be equal to data.eloc x to x plus window length. So on the first iteration, this is going to grab the first 240 bars. On the second iteration, it's going to grab from the 24th to the 264th, so on and so forth. So now we just need to put this data in here instead of using our main data open, high, low, close series. So I'll fast forward through this bit here while I just replace all these with window data. So there we go, I've replaced all of these references to our main data frame here with references to window data, which only contains that 10-day period. And so now it's going to run the backtest over that 10-day period and then move on and do the next 10-day period, so on and so forth. Now we need a way to actually get the results here from this backtest. So to do that, I'll create a returns list here. Returns is equal to just an empty list. And then at the end of each iteration, I'll append the total return to that list. So we can do something like returns.append pf.total_return. And then at the end here, we can print out the average of the total returns. So print, well, take the sum of returns and divide that by the length of returns. And that'll give us the average return for our strategy. Average return. Let's see what that spits out. As you saw there, despite the fact that we did maybe 1,000 backtests there, it only really took 2 or 3 times as long as it took to do one backtest. Again, that's just a quirk of VectorBT and how things work behind the scenes. So if you've got lots of backtests to do, it can be best to just do them all at once. Now, as we can see here, we're getting an average return of minus 0.8% over any given 10-day period during this time, meaning this strategy isn't actually working in any meaningful way. It's just giving us nothing. Now you might want to look at some other metrics, and for that there is a page in the documentation which I suggest that you go to. If you go to portfolio here and then base, scroll down a bit, you get to metrics, and this gives you all of the different metrics that you can pull. So for example, you can pull the total return using total_return. You can pull things like the max drawdown by using this function. You can pull the total trades, various other things. You just want to use whatever is here at calc function most of the time. So if you want to grab something like the Sharpe ratio or the worst trade or various other things, you can grab them using this function here. Okay, so just to establish a baseline here, let's compare this with the basic returns. So if I go back here, we can maybe come along and go over here. And so we'll say basic returns. So these are the returns without our strategy, and then we'll call this strategy returns. So strategy returns dot append, and then we'll change this one as well. Okay, and so we'll want to return the benchmark returns here. And so how do we do that? Well, we can just append the return to the list. And how do we get that return? All we have to do is we divide the final value in this data frame by the opening value and then -1, and that'll give us our returns. So we'll do basic returns dot append. Then we'll go inside another set of brackets. We'll do window data dot close, and then we want the final element, so .eloc -1. We'll divide that by the first entry, so window data dot close dot eloc 0. Close the bracket and take 1 off the whole thing. That will give us our basic returns here. We're just taking the final close, dividing that by the first close, and then -1. Okay, so we'll differentiate these. So this is our strategy, and this is going to be the benchmark. So it's going to be basic returns and basic returns. So let's see how our strategy compares to the benchmark across 1,000 different backtests here. So it looks like buying and holding during all these time periods would have returned you an average of about 1.4%, whereas the strategy is giving you a negative return. So we can see that our strategy isn't exactly optimal here. Again, you might want to do some deeper dive into maybe whether it's keeping us out the market longer, it maybe doesn't have as much volatility, but to be honest, with a negative average return, this strategy doesn't give me much hope. And so the final thing that I'm going to check here is just to make sure that our trades are executing properly. To do that, I'm just going to go back to my first example here. So this is the simpler version using the Y finance data. And what we can do is we can pull out the trades record here just to make sure that things are working as you might expect. So if we go trade records is equal to pf.trades.records readable. And then we'll print those out. So we'll print trade records. We'll want to sort them by entry just to make sure that we can actually read them in order. So sort of values, entry, timestamp. And then I'll do a .to_string to make sure it prints out the whole thing here. So here we go. I'm gonna have to zoom way out here. So we're entering here on the 18th at 1 p.m. and the average price was 19,182. So we'll check this against our data over here and just see what that looks like. So we'll grab both our hammer data and our price data here to make sure we're entering at the right time. We'll copy this and then let's zoom back in so we can actually see what's happening. And then instead of printing buys, let's print buys. Buys.index is equal to this time. And we'll do the same for data here. So we'll do data.index is equal to this time. And that should give us the right data here. So we got a true at this time and it was 19,182. 19,182, which is the right value. So that's how you'd go about checking your execution data. Again, that's going to be slightly different for stocks, so do bear that in mind. So that's a wrap for this introduction to programmatically reading candlestick patterns using TA-lib and VectorBT. I hope you've gained all the skills that you need to go out and implement this in your own strategies and build bigger and better models because of it.